Hey, John here. Let's talk about verifying that our board is working correctly. And to do that, I've created a bunch of test routines, starting with our favorite Blinky app. Now, I'm on a Raspberry Pi here. I set it up according to the scheme that I went through. I got a video posted on how I did that. See the links in the description below this video for the playlist for the Z80 Retro series. And in there, you'll find how I set up my Raspberry Pi, what apps I loaded, and how I did it, and all that fun stuff. Okay. I then cloned the Z80 repo and the Z80 programmer repo for this project here. And in here, you'll see there's a Pi directory, site make world. This compiles the Flash programming app that we're going to use in here. And in here under the directory tests, you see a bunch of assembly language source code files, all right? And then there's a README file that tells you what to do with these. Among other things, compile them all, assemble them all, I guess I could say. And then when you're done with that, you can use the programmer that we just compiled that comes with the Pi Retro programmer repo download, and then you can give it whatever binary file you want to program. So type make, and it'll assemble all these files, all right? Among other things, we see Blinky 1, Blinky 2, Blinky 3, all right? So this video is going to cover the Blinkies, okay? So let's look at Blinky. Let's start with the easy one. Blinky 1. We just need to see if this thing works in any way, shape, or form. Okay, so it's a listing file. Let's look at the source file. It might be easier to see what we're doing there. Blinky1.asm. Okay. This is going to be assembled using the Z80 ASM assembler. There's several assemblers out there. This is going to be cross-assembled. I'm going to run the assembler on the Raspberry Pi. It's going to generate a raw binary file that is byte for byte what belongs in the flash chip starting at address 0. Because when you give a hard reset to the Z80, it loads the program counter with 0 and expects to start running instructions there. And these are the instructions that will be there when we want to load and run the Blinky 1 app. So let's look and see what's going on here. First thing we do, we say include io.asm. Well, let's see what's in there. This is a file of nothing but equates. So there's no instructions in here, just equate statements, all right? So they include GPIO in, GPIO out, printer data, and so on. If we remember back to the schematic here, we can see that the GPIO port, this one here, the general purpose output port, I should say, is this latch here. There's a printer data port, and there's a general purpose input port up here. Each of these ports are controlled using this decoder. The output port over here you can see is enabled when IO request 10 is true, when it's low, which is when the Z80 does an input or an output instruction on ports that begin with 1. So that'll be 1, 0, 1, 1, 1, 2, 1, 3, and so on. We talked about this when I went over the schematic and the ports and stuff like that. Bottom line is the equate statements for the GPIO output port, the GPIO input port here, which would be IORQ0, okay? And the printer port down here, which would be on IORQ20, that's where these numbers come from, okay? So GPIO in, out, and data are the port numbers based on the schematic design, 0, 10, and 20, okay? Now, there's also port values for the SIO and the CTC. We'll talk about that in another video. The flash disable magical port that if we read from it or write to it will cause the flash chip to shut off and the Z80 start running out of the SRAM. That's at port 70. All right. Safety tip, don't do this until you're ready, okay? Down here, we need to see these as well for this application. You've got master out, slave in, you got the clock, the slave select, the strobe, and then you've got the bank select, the low bank address bits in here, right? And the 01248, you can see 1 bit at a time in your mind is on in each of these hex constants. Those bits match the bit assignment on the GP output latch here, right? So bit 0 is Mosey and bit 1 is clock and so on, up through 7, which is A18. And you can clearly see that matches in here. That's bit number 7, that's bit number 6, and so on. All right? Bit number 1, the least significant bit in hex is a 0, 1. The next most significant bit in hex would be 0, 2, and so on. So that's what we get out of this file. We get these which bit positions these various signal names are assigned to. So the first thing we do is we use them, okay? So what are we going to do? We're going to load the accumulator with a constant. So there's going to be a load immediate accumulator with whatever we get from Mosey or with strobe, okay? Again, you can go refer back to here or the schematic to see what that should be, right? So Mosey, that would be the least significant bit, and the printer strobe bit right here would be on. Now, I set both of these things to 1s so that the printer, if it happened to be plugged in while we do this test, doesn't go insane, nor does your SD card. Newsflash, don't plug in an SD card, don't plug in your printer when we do this test, okay? Because in theory, it could foul up your SD card or something, or waste a lot of paper. So the key here is that the SSEL bit is 0 when we do this, all right? And because of that, when we take that value and we write it into that output port and store it in that latch, the LED will go on, because the LED goes on when SSEL is a 0, okay? And in this expression here, it's 0. When we're done with that, we load HL with 0, and then we go into a delay loop, okay? So it starts at 0, we decrement it, and it only has 16 bits, so when you decrement from 0, you get all 1s, which is FFFF. We load A with H, or it with L. This is a very standard thing you see in, you know, the Intel 8080, 8085, Z80 type chips, where you want to know if the HL register is 0. You put the high register in the accumulator, or the bits with the low register. If any bit is set anywhere in HL, in other words, it's not 0, then the accumulator will have been left with a non-zero value after this OR operation, and the accumulator will, the ALU will have set the flags after this instruction as well. The key here is that DEC-HL does not set any flags. It's kind of annoying. So we have to do this in order to figure out if it decremented itself to a 0. You then, what do we got? Jump if we have non-zero value after this operation here, back to delay 1. So this counts up to 65536, as that's what it does. It just wastes time. After which we load the accumulator with the exact same value we did here, except now SSEL is a 1. And we know from the schematic, SSEL goes through this gate here. I explained this when we talk about the schematic. This is just here to be a buffer, and it happens to invert SSEL, right? So disk LED, it turns out, will go on when SSEL is a 0, and it'll go off when SSEL is a 1. And the LED being up here, right? So when disk LED is a 1, that LED will go on, okay? And disk LED is 1 when, because there's a not right there, when SSEL is low, all right? So whenever the SSEL selects the SD card, the LED goes on. Okay, so we then output that and store it in the latch. We count up to 64K, and when we're done with that, we go back to loop, which turns it back on again. Wait, off, wait, on, wait, off, wait. And that's the whole app, okay? So we just assembled all this stuff, and I didn't break anything. If we look at the README file, it makes it handy to copy and paste this. If you set up a Pi like I did, and you have compiled, or you've cloned, I should say, the programmer, the retro board programmer GitHub repo into your home directory, okay? then you can just type this in, assuming you compiled it, and you can load up whatever binary file you want to run. And we saw this in the Flash Programmer video. You can see it downloading the bytes, and then it validates it and says everything looks good. And we can see that the LED is flashing. And the visible rate that you see it flashing at should give you some clue at how fast or slow a Z80 really is, and how long it takes it to count up to 65K. All right? So that's all there is to Blinky 1. Let's now go look at Blinky 2. Now in this app, what I'm going to do is I'm basically doing the same thing. However, before I run the program, I'm going to do this. And this is us testing now our ability to switch from the flash to the SRAM. All right, so to do a quick recap, remember the SRAM and the flash, these two objects here are controlled by this system up here. Whenever we reset the Z80, this is true, okay? In other words, reset goes low. And when that happens, flash shell becomes low and SRAM cell becomes high. And that stays that way until IO-Rec 70 goes low. And IO-Rec 70, as we saw a moment ago, comes out of the port decoder. As long as we never touch port 70 here, okay? What that means is that whenever the Z80 is executing any read operation, whenever it reads from memory, flash MREC will be true, okay? Because flash cell is low after the reset, and whenever Z80 wants to touch memory in any way, it asserts MREC. So when MREC is true because it wants to do any I/O, and flash cell is low, this will go low. And this, remember, is connected to the enable on the flash. If the Z80 is reading, then great. It will assert read, and the flash will supply the data that the Z80 wants. And while this is going on, keep in mind that SRAM cell here is 1, right? Because after reset, this is a 1, that's a 0. So no matter what read is, SRAM OE must be 1. It stays 1. It will never become 0. It'll stay that way forever until somebody touches IO-Rec 70 over here. All right, so this is this weird asymmetric startup stuff that we talked about before. And in this mode, the flash chip gets enabled on all memory requests. And the Z80 read and write signals are connected directly to the flash. So if the Z80 reads, it reads from the flash. If it writes into the flash when we're in this mode. Okay? Now, notice the SRAM is also connected up to MREC. So whenever the Z80 does a read or a write operation, it will also enable the SRAM. It seems a little bit wonky, but keep in mind that SRAM OE, which comes from this circuit up here, when we're in this reset state, as I said a moment ago, is always a 1. So whenever flash MREC goes low, because the Z80 asserted MREC, right after the reset, both the flash and the SRAM will be enabled, but you can never get any data out of the SRAM because this is pegged high, okay? And if the Z80 ever writes anything, it will write it, the flash will accept the data, and the SRAM will also accept the data at the same time. So what do we know? Right after a reset, anytime the Z80 reads anything, it gets data from the flash, period. Whenever the Z80 writes anything, I should say whenever it reads memory, not anything at all, just if it reads memory, the flash will supply the data because MREC will be low and read will be low, and flash will send the data back to the Z80. The SRAM OA will never be low at that time, so the SRAM will just sit there. If the Z80 ever writes any data into memory anywhere, it will write it to both the flash and the SRAM at the same time. Flash doesn't care unless you put it in a programming mode, and we talked all about that when we talked about the flash programmer, okay? And we're not going to do that, so that doesn't matter that this thing is hooked up this way, all right? The flash will simply discard it. All right, so what else weird is going on here? Well, remember the SRAM is hooked up to all these OR gates over here. I talked about all this before as well. Whenever A15 is high, in other words, we're accessing memory whose address is greater than hex 8000, it forces every single one of these bits here to be ones, which is hooked up to the address lines on the SRAM. Therefore, if you mentally divide the SRAM into 16 banks of 32K each, because it's a half a megabyte, whenever the Z80 wants to address the high half of memory, it will always get that top bank number F in hex. Whenever it's addressing anything in the low half of its memory, A15 will be 0, and the address bits that comprise, that define which bank of memory will be read or written, will be defined by the values in these low bank A15, 16, 17, 18 bits. And those come from this latch down here, which is the same latch that we were just playing around with a minute ago with the LED. All right. So if we set all these to 0, anytime the Z80 interacts with the static RAM, when A15 is a 0, it will be accessing an address where A15, 16, 17, 18 are all 0. Okay? And if the Z80 ever talks to any memory address greater than hex 8000 and including, then it'll be high and we'll end up with the top bank. Okay? And all the other banks won't get used. All right? And that's what we're going to do in this scenario. So the first thing we're going to do is what? We're going to set MOSI, SSEL, and strobe. In other words, we're going to put zeros on all those bank select address lines. The low bank, A15, 16, 17, 18 are all zeros. The MOSI, SSEL, and print strobe are high. So that's what we're going to put in that latch. And when we're in that state, we're going to do this. We're going to load HL with 0, DE with 0, and BC with whatever that thing is, right? And underscore N is down here. It's a label that represents the very last address that's in use by this program. Okay? So what does this thing accomplish? The LDIR instruction says copy 1 byte at a time from a memory whose address is in the HL register. So it's going to read that, and then it's going to turn around and write it into another memory location whose address comes in the DE register. And because they're both starting in the same place, what this is really going to do is it's going to read a byte from 0 and write it back into 0. And every time it does that, it subtracts 1 from the BC register pair, which is loaded with, for all intents and purposes, the number of bytes in this entire program. And if the BC register pair ever goes to 0, this instruction will stop. If it's not 0, it'll increment the HL register, it'll increment the DE register, and it'll repeat itself. So what this is going to do is it's going to read from 0 right to 0 and count it. And it's going to go back and add 1 to HL and DE. And it's going to say, read from 1 right to 1, and then count that over and over and over and over and over until underscore N number of bytes has been copied. When we've done all that, this is where we're taking advantage of the fact that the OE will never go active, but the write does go active when the Z80 writes to its memory. So what's happening here is we're reading 1 byte at a time out of the flash from address 0, 1, 2, 3, and so on. And then we're writing them 1 at a time, oddly enough, back into the flash, who, like I said, ignores them and throws it away, and at the same time writes them into the static RAM at this same address that they came out of from the flash. Now, we could do all 64K if we wanted to, but there's no point. We only need to go as far as there is data that we care about in the flash, and that is only from 0 up to underscore N, which we saw as the end of this file. All right, so that's what that thing does. When it's totally done, we can now read from port number hex 70. And when we do that, that's the first time this will ever go low, right? Because it comes out of the decoder over here. If I ever access port number 70, this goes low. The other ones will be high, okay? When this is low, this thing flips over. This becomes 1 and stays there forever until reset goes active again. When this goes 1, this up here goes 0 and stays there again until reset goes active again. So in this state, when flash cell is pegged to a 1 forever, flash MREC can never go low ever again. 1 ORed with anything is always 1. And that flash MREC, remember, is tied to the chip enable on the flash. The flash will never get used again once we're in that state. Right? We're kind of like Hotel California in reverse here. We've left and we can never go back. And in this state, remember that this is going to be 0 and stay 0 forever. Well, once that happens, the SRAM OE signal is just a copy of the read signal over here. Okay? So once that thing flips and we touch port 70, SRAM OE is simply the read signal from the Z80. So now the Z80 can read and write from the static RAM. So that's what this thing does here, right? And these giant comments, note that we can't read from the SRAM in here, okay? What's the big takeaway? Don't call a subroutine because you have no stack. Or more accurately, there's nothing that you can't store anything in a stack that you can then read back until you turn on the static RAM, okay? So that's what's going on here. We copy all the data from the flash to the static RAM. Then we can call subroutines and have fun. Let's load the stack pointer with a useful value. Stack top, which I normally set to 0, right here, okay? Logically speaking, that's the highest address of the memory, plus 1. It'll wrap it back around to 0. And this is what do we call this? A full descending stack. So setting it here is really the logical top of the stack when the stack is empty. Okay? So then what do? We're going to basically do the exact same thing we did before, but rather than hard code the delay loop in our code here, we're going to call a subroutine. Right? Otherwise, this is exactly doing the same thing, right? Call delay, then we do turn it off, call delay, and then we go back to a loop. So we're a little easier to read the code. The delay logic is exactly the same as we saw before, except for this value here. We don't load HL from 0 and count down all the way around to 0, which would be 65536 iterations. We load it with 8,000, which is only 32K iterations. It's half that. And I did this on purpose because sometimes, when you build and run a program whose output, manifests itself in the exact same way as the last program you run, especially if you're programming a flash or something like that, you have absolutely no way of knowing whether you're looking at the new program or the old one. As I could have accidentally reloaded the old one by re-executing this, for example. Believe me, these things happen. So by changing the rate of flashing, we can now tell whether the old one is still running or the new one is running. And voila, you can see that the light flashes at a different rate. All right, so far so good. We know the flash works. We know the SRAM works. We know that works because if we couldn't call and return from a subroutine, this thing would be completely failed. We know the reset circuit here works. The bank select may or may not work. We'd have to put a probe on there to know whether these bits are what we told it to be or not. It's probably okay, but don't trust anything until you see it with some sort of a logic probe or something. The thing is probably okay because if we can flash the LED down here, We know we're in control of this pin right here, therefore we're probably controlling the latch properly, that the address works, it's probably hooked up right, and so on. We know the I/O port decoders are working, because otherwise none of this would work, okay? So let's look at Blinky 3 and see what this is going to test. We do the same thing with IOASM, stack top 0. We do the exact same copy to underscore end, and underscore end is still at the end of this file down here. So what does the rest of this program do? We set up the stack. What do we do? Idle the control signals that could matter. Again, don't put your flash card in, and don't plug a printer in during this test at all. That's for really sure. Because what are we going to do? We're going to use the B as a counter to see the printer data lines changing in a recognizable way. So what we're going to do is we're going to say what? We load A with Mosey and we turn on the LED. We turn the LED on because SSEL is not set in this value here, okay? Send the counter value to the printer data port. So I'm going to say load A with B, which was 0 from up here. We're going to just output it there. We're going to increment B. We're going to call the delay routine, which is the same as before, except now notice the delay has gone down again. Again, we've changed the flashing rate for our LED so that we know that this program is the one that's running. It's not the previous one. And we have to blank faster. We'll fix that while we're here. So that the counter doesn't take forever either. So what else is going on in the loop here? So we call the delay. Waiting a short amount of time. We turn on the LED, or we turn it off in this case because that's a 1. Then we say output out the printer data latch, the value from the B register. We increment the B register here. We wait again. And then we go back to the loop here. So what happens is the value in the B register, every time we turn the light on or off, we increment it. And we output it to the printer data latch. All right, so in binary, we should see a counter going moderately fast-ish on the printer port bits. And we can poke a logic probe on there and make sure that they all work correctly. And by working correctly, I mean we can verify that if we're just going to be counting in binary here at a relatively fast speed, the data bit 0 should be flashing as that code is written, actually, the same speed that the SSEL LED is going on and off, by the way. Then the printer bit D1 should flash at half of that speed, and 2 half the speed of 1, 3 would be half the speed of 2, and so on, to the point where this one down here is it takes like 128 times of flashing the SD card LED over here between each time that D7 would ever change its value. All right, so this would let us know that we hooked up the data bits in the right order. All right, now usually that's not a problem when I lay out a PC board, but sometimes I get the bits out of order when you're wiring these up by hand. Notice these pins don't just go 1, 2, 3, 4, 5 over here. 3, 4, 7, 8, 13. You can screw this up sometimes if you're doing this by hand. All right, so never underestimate your abilities, no matter what it is, okay? So let's go ahead and fire this up, and we can make a quick hack, homemade logic probe, and we can poke around on the data bits for the printer port and see if it's doing this stuff. So the first thing we want to do is get our little programmer going here. And then we say less than, and this time we're going to load Blinky 3. And the first thing we notice that the flash rate has increased, quite obviously. So if you don't have a regular logic probe, in this case you can make a real simple one. We just care if it's 1 or a 0. We don't need flashing for changing and all that other fun stuff. So what I got here, I got what looks like a 1K resistor. You could use a 680 or a 470 or whatever. I think there's a 1K, so it doesn't get too bright because the camera doesn't do well when the LEDs overbright the lens here. And I've got these two wires. So the green one is hooked up to the negative side of the LED. So if the green is ground and the yellow is 5 volts, enough current will flow through here to light up that LED. All right. Now the printer port, I happen to know all the pins along here are connected to ground. So we can just stick that on there like that. And pin 1 here is the printer strobe. So let's have a look, see at the value of the printer strobe. It's flashing along with that one. Now the reason for that is because I overlooked it when we looked at the code a moment ago. This right in here, the printer strobe value goes on and off along with the SSEL. So that matches the SSEL output, okay? Now, as we move along the printer port, the next pin, pin number 2, is connected up to data bit 0. So that is also flashing at the same speed as the card select, all right? Now, as we move along, you'll notice it's flashing half the speed, right? Half the speed again. Half the speed of that. Half the speed. Now it's getting so slow, we're going to have to sit here and wait a little while for it to go on and off. These are all good signs. It's working. Okay. So far, so good. I don't know how many we've done so far. Is that 1, 2, 3, 4, 5, 6? This is number 7 of 8 total bits. All right. You can see that's taken quite a while. The next one's going to take twice as long as that. So I just went on. Now it's off. I think we're having a successful situation here. So I think we successfully verified that all 8 of the output bits on the printer port and the printer strobe works. And it all makes sense. So each of the bits that's going on and off must be connected to the right bits coming off the data bus from the Z80. Now, we didn't set them to anything in particular, but let's have a look, see at what the line feed output bit is set to right now. It happens to be high. Okay. Now remember, that is a this wonky output bit that kind of we snuck from the SIO port, right? And then another bit that we snuck from the SIO port is the init bit, which is right there. So both of those just coincidentally happen to be a 1 right now. Now yours may or may not do that. I don't know. It depends on what code you may have run on your board before you rebooted it to do this test, and what happens when you reboot an SIO. I don't know. 2, 3. The fourth one down here is the select output, which is supposed to be a 0. And lucky for us, the LED's off. So the schematic wiring and my recollection of what's supposed to be what does seem to be correct. Now, all these other ones are supposed to be connected to ground, and they are all LED off, so they're all 0s. That's a good sign. And these last 4 over here are hooked up to things like the printer status. These are inputs, and you can actually see, I don't know if the camera's picking this up. Yeah, maybe a little bit. That the LED goes on really dim here. That's a very good sign. Why? Because these pins all have pull-up resistors that are 10K on them. That looks really good. And this is, of course, the high-order data bit. All right. So the 4 bits that are inputs very dimly light up the LED, and all the outputs that are supposed to be outputs are all doing recognizably correct things. So I think we're doing pretty good so far. The purpose of these test programs, remember, is to make sure that the board works. So what have we learned? We learned that the Z80 actually is executing code. We can recognize it as working. We know the flash works. We know that the SRAM works. We know that our reset logic works, and that the flash can be copied into the SRAM. This probably works. We probably should have poked around with our little homemade probe to verify that these are all 0s. But the reality is, if the Z80 is interacting with this over here, and it is, keep in mind where the stack data is. The stack data is kept at the highest addresses in the SRAM. So A15 will be going on and off, and these will be going between all 4 zeros and all 4 ones as it leaps back and forth. Now, unfortunately, my logic analyzer broke recently, and I can't just clip that on here. Otherwise, we could take a really nice picture of that, but not today. We know the port decoding must work because we can turn on and off the flash and SRAM modes, which means we can touch port 70 and cause the memory to go on and off. We know that We know that the IOREC 10 works. We know IOREC 20 works because we are able to update those registers, these two latches. The printer data is hooked up and runs correctly. We know that this strobe here, the SSEL line, lights up that LED. We don't know for sure that these other signals are working correctly, but we can strongly suspect that they are. But, unless you actually clip on here and really see with your own eyes, or write absolutely definitive test programs to verify that these things are all doing what they're supposed to be doing, you don't want to bank on this, okay? What else do we not know yet, right? We haven't tested the general purpose input port yet. And we haven't tested this. What else do we got on here? We have not played around with the counter timer chip here, okay? And we haven't played around with the SIO chip over here. Now, these are a little more complicated. We're going to have to look at the data sheets to make sure that we all understand what the commands and controls do to get these to get into the right modes, because these all have what mode do you want, or which of the 4 counters do you want to do this, and do you want interrupts on or not. These are more complicated, so they'll take a little bit more setup time and think time to get the code to work, for us to understand what we want to do with the code, right? This down here is just a simple driver. We'll test this when we test the SIO. The SD card. The SD card bits are going to require a little thinking. This is probably going to be the subject of a couple of videos on its own. Getting an SD card online and talking and configured is a little bit more work. It's not as simple as just, here, send data to a printer port. So we'll have to give a little more thought to this, okay? We'll do this one last, all right? So when we come back, what we'll do is we'll play around with the SIO. Because once we got the SIO going, we can actually print something on a screen. We can display data. And we can, write hello world programs and stuff like that. So SIO is definitely the #1 thing next on my list, okay? And if you think about it, we can write a little loop that could read data from the general purpose input port and print out, hey, I see these values on these pins. We can also print out things like, hey, I just selected bank number 0, and then you can go there with your probe and you can, poke around in here to see that that's the right one. It makes debugging easier if you can print stuff out, is all I'm saying. And then after that, we can play around with the timer. So, something to look forward to next time. Thanks for watching. See you later.